Good evening. My name is Tansu Demercy, and I'm the software engineer responsible for Archangel's communication protocol. Today, I'll be demonstrating this protocol and explaining how it works. As you may know, Archangel has chosen the Gimme Fast project, which revolves around transmitting data between two terminals using visual light communication and a vehicle for transportation. Lucky for us, we'd already finalized the circuitry designs for LEDs and LDRs before the whole social isolation measurements were taken. This means that we'd already chosen the baud rate at which we were going to work, and we also had already tested the error rate which this would introduce. The baud rate we had chosen was 30,000, since this is fast enough to stay within the 2-minute time constraint we have for the entire data transfer, while also introducing only a very low error rate of 4%. Now, since we're unable to physically access the circuits right now, I've instead introduced another function to the communication protocol, which is going to corrupt the data at a rate of 4%. Allow me to share this with you now. Here we go. All right. So, as you can see, a random number between 1 and 100 is chosen. This number is compared to a constant probability, which is defined up here, and is equal to 4. This means that the if loop is entered with a probability of 4%. If the if loop is entered, then the data will be corrupted. Please note that this is checked on a frame basis, and the 4% data rate that I'd mentioned earlier was also on a frame basis. If the corruption data function is accessed, then another random number is chosen to determine how many bytes of the frame are going to be corrupted. Now, I've already mentioned one of the requirements that we're facing, which is the 2-minute requirement, which we're making sure is being met by choosing the baud rate high enough. We've also got another requirement which says that at least 5 trips are needed for the data transfer. Moreover, only 10 kilobytes of space are allowed to be used on the vehicle for this process. This means that the partition size needs to be chosen according to the size of the file to be transferred. The file size in kilobytes is compared to 50. If it is less than 50, then we need to make sure that we have at least 5 packets by dividing it. Now we're rounding up during this division, and of course it's not going to be divisible exactly by 5, so the first 4 partitions are going to be equal in size, and the last one is going to be different. Next, we have the condition when the file size is more than 50 kilobytes, in which case we're going to separate it into equal partition sizes. Again, the last partition size may differ here. Now that we've covered this, I'd also like to point out that my laptop does not have any serial receiver transmitter ports as a Raspberry Pi would. To overcome this and still be able to do the whole process on serial communication rather than opting to byte-wise transfer, I've downloaded a virtual serial port driver. Each of these comms is going to simulate one output or input which is connected to a LED or an LDR. This allows for the whole process to emulate the same process we would have otherwise used. It also means that the code only needs to be adapted very, very slightly, which means just the names of the comms. And of course, the data corruption process needs to be taken out if the code is going to be run in real life. Moreover, as you might have noticed, we have a lot of comms, a lot of LDRs and LEDs. In fact, we have exactly 16, 8 of which are LEDs and 8 of which are LDRs, which is the maximum we're allowed to use for this project. We've decided to use all of them and apply multi-threading to use multi-channel communication. Each of the data transfers is going to be done over 3 channels rather than 1, which increases our data transfer speed by 3 without increasing error rates. Right. This then brings me to the frame layout. Now, as I've already mentioned, where's my frame? I've closed my frame. I'm so sorry. Let me just, here, the frame, right. As I've already mentioned, we're going to divide the data up into 5. And because we're using 3 channels, we're going to divide each one of those 5 partitions into 3 more. Each of those 3 remaining partitions then is going to be divided up into frames before transfer. It's going to be divided into 36 because each frame carries 36 bytes of data. However, we're also adding 2 bytes of sequence number, 1 byte of the number of zeros, and 1 byte of checksum. The sequence number is crucial for us because we're using 3-channel communication, which means there's a high chance that the data will get disorganized, especially if one of the frames gets corrupted, needs to be sent again. It's definitely going to be out of order. So we need to be able to sort it, otherwise the image is not going to be displayed correctly. The number of added zeros here is used because not all of the partitions are going to be divisible by exactly 36. In fact, most of them probably aren't. However, we need the frame size to stay constant, so we're going to add a certain number of zeros, however many it takes for this section to be 36. We need to be able to delete the number of zeros that we've added before displaying the picture, because otherwise it's going to be corrupted. So that's what this byte is used for. We've also got a checksum byte here, which is used for error detection. The way this works is these first 39 bytes are going to be divided by a key, which we've chosen to be 255, and the remainder is going to be added as the checksum byte by the sender. The receiver, upon receiving the frame, again does the same thing. It divides the first 39 bytes by 255 and sees if the remainder is the same as the checksum byte. If it is the same, then it accepts the frame to be error-free. If it is not, then it sends a message to retransmit this frame. Right. Now we're going to move on to running the code. Though before I do, I think it's important to point out that we've got compression happening at the very beginning. This compression was not done by me, it was done by Ikinaikut, and he's going to be talking about it in more detail in a separate video. However, it is necessary to do, here we go, because our initial image here is a BMP file and very large. As you can see, it's 900 kilobytes, and it's going to take very, very long to transfer. So what we do is compress it, turn into a JPEG file, and transmit that file. You'll see that happening when I run the code. So let's get right into it. I've already prepared all 3 of the codes to be run. Of course, 3 separate codes need to be run because in real life, there'd be 3 separate microcontrollers running these codes because they're, one terminal, one vehicle, one other terminal. So I've started the main vehicle code. I've now started the receiver code, and I'm now starting the sender code. We'll be able to see what happens. First of all, let me just show you how this test file has been converted into a JPEG file right here. It is now much, much smaller at only 43.3 kilobytes. And we'll be soon seeing a results JPEG folder popping up, which is going to be the JPEG which is received on the second terminal. Now, the reason for this taking so long is because I've added delays in between to kind of simulate how this whole process would look like in real life if the vehicle was going between the terminals. As you may see, where's my vehicle? There's my vehicle, right? See here, sleep. Yeah. Oh, I forgot this one. Okay, this one here is only 5. This one's still at 10, which I found to be very long, so I'd already changed it to 5. But it's okay. We'll just go with the 5 and 10. All right. So let's just see where everyone is at. Here you can also see the amount of data that is currently stored. This again is just to point out that, oh, right, I have messed up slightly. I'm sorry. Let me just restart this. I've made a typo, so I couldn't start. Oh. Communication protocol. Okay, so this one's starting. Here now. Protocol. Do this every time. And receiver main.py. This one's starting. One more. Communication. All right. Now, all of them. I forgot to delete this one. Well, we already saw that it worked, so we're just going to be using the same file as the one we created last time. But as you can see, it's already started transferring. This file right here is the file at the receiver end. As you can see, it's not completely done yet, only partially, and we're going to be able to watch as the data is transferred. Again, we see the file sizes, well, the space used on the vehicle. We see the ports being opened and closed. It's important that the ports are closed when they're not being used. This is because in real life, power consumption would also be a problem. So we would want to cut off the current, well, the power supply when we're not using anything. Right now, of course, it doesn't really make a difference. All right, so all packets have been sent by the first terminal, but not yet received. 1, 2, 3, 4, 5. Yes, we've gotten them all. So let's check the results file. As you can see, it is exactly the same as our initial file. Thank you very much for your attention. I hope you've enjoyed this demonstration.